The last thing we're going to look at is energy in simple harmonic motion. Whenever we're dealing with a mass on a spring, the object is at rest, the potential energy is going to be maximum, and the kinetic energy is 0. The potential energy we're dealing with for springs would be elastic potential energy. So in case you forgot, elastic potential energy, and you do get this equation, is equal to 1/2 K delta x squared. But for a mass oscillating on a spring, the amplitude is the displacement, so instead of delta x squared, we can say that EEL equals 1/2 K A squared. And this picture over here, I'm going to draw it a little bit differently later, but this picture over here just shows you what the energy is at each amplitude or each point in position. So not an energy time graph, but an energy position graph. And you can see you're going to have your maximum potential energy, that's the blue. Your maximum potential energy is when you're farthest away from the equilibrium. Kinetic energy is going to be the exact opposite of potential energy, so as one goes up, the other goes down, and you'll see this here. The total energy is staying the same the whole time. So at equilibrium position, the kinetic energy is the maximum and the potential energy is 0. Think back to the graphs that we were looking at. The block moved fastest at the equilibrium position, so that's where you'll have maximum kinetic energy. Because total energy is conserved and remaining the same, the maximum potential energy equals the maximum kinetic energy. So what that tells us is that EK will equal EEL, so 1/2 M Vmax squared, because your maximum kinetic energy is when your speed is at a maximum, will equal 1/2 K A squared. And remember, the amplitude is your maximum displacement. These 1/2s cancel out. We take M over, Vmax squared equals K over M times A squared. Rearranging to solve for Vmax, we're going to take the square root of both sides. Vmax equals your amplitude times the square root of K over M. So this is how we can figure out what the maximum velocity is using just energy. Okay, quick note about the energy graphs. I'm going to look at energy versus position and energy versus time. We'll start with the energy time. Make that a little bit straighter. Your total energy over the whole time is going to remain constant. So that's your total E. Let's look at the time in terms of periods. So we'll look at this over one period. This would be T over 2, 3T over 4, and T over 4. In the beginning, let's say you have an amplitude of your maximum amplitude. When you're at your maximum amplitude, your kinetic energy is 0. So I'm going to do EK in yellow. So you're at your maximum amplitude at T equals 0, at T over 2, and at your T. So that's where your kinetic energy is going to be the least. It'll be maximum here and here as you're going through the equilibrium position. So this would be your, let me redraw that. Kinetic energy versus time. Your elastic potential energy is doing the exact opposite. So I'll draw EEL in blue. When you're at your maximum amplitude, your elastic potential energy is greatest, and it's going to do the exact opposite that the kinetic energy did. That should not be straight. This is why I always write in pencil. Okay, so what these graphs are, we know that EEL is proportional to A squared, that's your X, our position time graph was a cosine function, so this would be a cosine squared graph. Your kinetic energy is proportional to v squared. That was a negative sine function, so this would be sine squared. So all your energy graphs they're cosine squared and sine squared. If we look at energy versus displacement, and you can actually see that in the picture that you have in your notes. It gives us negative amplitude, positive amplitude. This is where the amplitude is 0. So your kinetic energy will be greatest when you're at equilibrium position. It'll be 0 at the maximum and minimum amplitudes. Your elastic potential energy is 0 at the equilibrium position and maximum when you're at maximum amplitude. And your total energy the entire time is again going to be the same. That was drawn poorly. So your total energy will be about here. So those are the energy graphs. You do need to know how to draw these. I would do for both versus period and versus amplitude. Just know that the energy is directly related to the position for elastic potential energy and to the speed for kinetic energy. If you know how to do those kinematic graphs, you should know how to do the energy graphs. Let's do 3 really quick examples. First, it tells us the block oscillates on a very long horizontal spring. The graph shows the block's kinetic energy as a function of position. What is the spring constant? We know that the maximum kinetic energy will equal the maximum elastic potential energy. So 1/2 K A squared. We can see what the amplitude is just by looking at this. The amplitude is 2. It doesn't matter if you use negative because you're squaring it. So isolating to solve for K, we get 2 times the kinetic energy over A squared will give me the spring constant. 2 times 8 joules, reading that rate from the graph, over 4 meters squared equals K. 16 divided by 4 gives me 4 Newton per meter for the spring constant. So just a simple problem reading the graph. Let's look at the next 2, and again, these are going to go pretty quickly. We have a mass oscillating up and down on a spring. It shows us the motion over here. Where is the acceleration? 0. So remember, acceleration is 0 when you have no net force. You have no net force anytime you're at the equilibrium position. So this would be A, C, and E. Where's your maximum kinetic energy? Maximum kinetic energy is at the equilibrium position. So that's where your maximum speed is. So again, we have A, C, and E. And finally, where is the maximum potential energy? That's where it's at the highest or lowest point. So this would be B and D. One more, let's just look at a pendulum. So a pendulum is going to have gravitational potential energy as opposed to elastic potential energy, but it'll work the same way with the graphs. So where is the acceleration? 0. Acceleration is going to be 0 at equilibrium, so that would be B and D. Where's the kinetic energy and maximum? Again, at equilibrium, so B and D. And finally, where is the potential energy and maximum? A, C, and E, where it's at those maximum heights. So that's about it for energy. This is mostly going to be conceptual, and we will do some practice with this. Simple harmonic motion is not terribly hard in terms of the math or the algebra. It's more understanding the graphs and what's going on at each point in the motion.